We have looked at quantum Hall effect in a 2D electron gas such as silicon MOSFET or gallium arsenide. We have started looking at the same phenomena, that's quantum Hall effect, in graphene. So, graphene has its own interest for the reasons that we have talked about. It has a Dirac-like dispersion comprising of massless fermions. The low energy dispersion resembles that of massless Dirac fermions, and there are many things. The physical properties of graphene are by themselves very interesting, and we wish to talk about the quantum Hall effect in graphene, and there is a possibility that actually the quantum Hall effect is realizable at a very large temperature that is comparable to the room temperature, and this is what we are going to see. To start that, and before we actually talk about quantum Hall effect, we can look at the Hofstadter butterfly, which we have discussed earlier. So, we can look at the Hofstadter butterfly in graphene. So, the basic idea is that the electrons either in say the 2D electron gas or in graphene, say if they are particularly in graphene when they are described by the tight binding model, and then they are subject to the external magnetic field, they will show quantized Hall plateaus for the Hall conductance or the resistance, and consequently the band energies of the electrons transform into discrete Landau levels, and this is what we are going to find, that how the Landau levels look like in graphene. We have seen that already at length for the case of 2D electron gas. Now, this presence of this periodic crystal potential, which is the lattice basically, which means that V of r is equal to V of r plus r, this is the periodicity. So, this is a periodic crystal potential. Okay. It adds further features to the spectrum, and that is what the butterfly is all about. So, this Hamiltonian in presence of such periodic potential is written as P minus E A whole square over 2m and plus a V of r, and this V of r has this property that we have just talked about, and where r, capital R, is the lattice periodicity. And the electrons are described by the Bloch states here, where k is a good quantum number. So, we are talking about purely about graphene. This is not applicable to the 2D electron gas. So, in presence of this magnetic field or the magnetic vector potential, so this each Bloch band gets further divided into sub bands, and this resultant energy spectrum as a function of the magnetic flux, it gives rise to a fractal structure which is known as a Hofstadter butterfly. Okay. So, this rather complex looking energy spectra, it arises because of a delicate interplay between two length scales of the problem. This is a very important statement, and so these two length scales are A and LB. So, A and LB, and these two length scales where A is the lattice constant and LB is the magnetic length, which we have said a number of times earlier. So, it is basically the interplay of these two, and the Hofstadter butterfly, it basically arises when this ratio of these two, A and LB, is a rational fraction. In fact, more interesting physics arises when the ratio is not a rational fraction, but an irrational fraction, but of course, we will not discuss it here. Okay. So, this fractal nature of the spectrum was first discovered or rather seen by D. Hofstadter, and that is why it is called as a Hofstadter butterfly in 1980. Okay. When he solved what is called as a Harper equation, We'll come to that, but let me not go into details of the Harper equation. And he demonstrated that for commensurate values of this flux, so which is phi over phi 0. I told you that the phi 0 is a very important quantity, it is h over E, which is the quantum of flux. If this becomes of the form P by Q, where P and Q are co-prime integers, and what is meant by co-prime integers is that there is no common factor between them. If the flux because of the external field is such that, then these the single particle block bands they split into Q sub bands, okay, and these sub bands are themselves p-fold degenerate. This is a very important thing which is needed for these butterfly or these fractal spectrum to take place. And as I said that there are two length scales in the problem. One is the lattice constant, which is basically the periodicity of the lattice, which is written as r plus r. So, r is equal to nothing but this is equal to a, that is the lattice constant, and LB is the magnetic length of the problem, which we have said earlier, it is root over h over EB, and the ratio of this will decide what kind of spectrum we get. And it turns out that this is related to the fact that these phi over phi 0, these are in a form of a rational fraction, P by Q being integers, co-prime integers. So, what happens is this, that each of the block bands would split into Q subbands, and each of these subbands themselves are p-fold degenerate, okay. And each of these p subbands they further split as a continued fraction as a function of this magnetic flux. That means when the magnetic field is varied, it forms a continued fraction. So, if you want to know what is a continued fraction is written as, say for example, so this is a continued fraction. So, this A0 plus a 1 by A1 plus a 1 by A2 plus a 1 by, this sort of goes on, and then there is a plus 1 by an kind of thing. This is called as a continued fraction. So, these each of the p subbands they split into these kind of a continued fraction as a function of this flux phi over phi 0. So, I give you an example, 181 by 101 is a rational fraction which can be written as 1 divided by 1 plus 1 plus 1 divided by 3 plus 1 divided by 1 plus 1 over 4 plus 1 by 4 and so on, okay. So, these are some examples of this continued fraction. So, this is what happens. So, this distance between these levels or these the sub levels etc., and the width of each of the these superstructure they oscillate with as the magnetic field is varied, and the period of this variation of this quantity, basically it is universal, and it does not depend upon the particular form of the quasi-particle dispersion etc. Okay. So, this is well known, we have talked about this. I thought of repeating this of these fractal structure in the case of graphene, because we have earlier talked about in a different context, okay. So, let me show you that how we calculate these Hofstadter butterfly for graphene. So, let me take a lattice, a graphene lattice or a honeycomb lattice with 2 atoms per basis, these red and the white atoms. For the sake of clarity, we have taken these lines which correspond to m minus 1, m plus 1 and m plus 2 in the sort of vertical direction, though it is slanted, and then we have also taken these the horizontal lines as n minus 1, n plus 1 and n plus 2 and so on. And so in order to demonstrate the Hofstadter butterfly, we take a ribbon like this, and this is called as a semi-infinite ribbon. Okay. So, this is the semi-infinite ribbon, and now we will do this calculation. It has zigzag edges. This is important in the context of graphene, that there are two kinds of edges. This is called as a zigzag edge, because as you see that this looks like a zigzag pattern, and that is why it is called a zigzag edge. The zigzag edge on one edge, that is one side, means that there is armchair on the other. So, the armchair pattern looks like this. So, this is the armchair pattern, and so on. Okay. So, we have taken a zigzag edge, and the prescription is clear. We need to change the mechanical momentum of the electrons by including the magnetic vector potential using Piles coupling. So, we will use this exponential I e over h I and j a dot dr, say for example, and a t I j. This can be written as exponential I 2 pi by phi 0 and I to j and a dot dr and Tij. So, each of the hopping integrals they get modified. So, Tij get modified, each pair of the hopping integrals get, or the amplitudes get modified by this. So, Tij is the one without any field. So, the information about the field is coming from these exponential term or the phase. Okay. And of course, we know that phi 0 is equal to h over E, and we have again taken B to be in the z direction, that is the transverse magnetic field that we have always said, and B is a constant. And we can take a Landau gauge where this is written as B x y cap. We have shown another choice of the gauge, another Landau gauge, so to say, which is minus by x cap, but they would of course yield the same result. Later on we will talk about a third gauge, which is called as a symmetric gauge, which is important for a different reason. Okay. So, once we fix this, so let me write down the tight binding Hamiltonian. So, now in the tight binding Hamiltonian, the kinetic energy or the hopping amplitude would now get modified by this vector potential, because we have an external magnetic field present in the problem. So, just to show you again, I will write it first and then we will go back and show this. So, m and n are the pair of sides. So, t exponential I pi phi over phi 0 and n and a m n dagger b m n plus t exponential minus I pi phi by phi 0. Of course, there will be both the signs present, and a m n dagger b m minus 1 n, and there will be another term which is t m n dagger b m n minus 1 and plus Hermitian conjugate. And you see that the hopping along the x direction is picks up a phase. This is m n and b m minus 1 n, and I will show you the picture, that is this. So, these are these coordinates of this. So, one of them, so this one has a coordinate which is say n plus 2 and m minus 1. Okay. So, rather because of the gauge that we have chosen, the hopping in the y direction is affected, because this is along the y direction, and in the x direction it is not affected. Okay. And a m n and b m n are these electron creation operators. I mean daggers are the creation operators. So, a dagger would be the creation operator, and so this A is annihilation, and this is in A sublattice, and same for B. So, B dagger and B are creation, annihilation operators in B sublattice. So, I think it is clear how these Hamiltonian is written, which gets modified by these presence of the external magnetic field, okay. And a site index, each site is represented by two numbers, because we are talking in two dimensions, it is m and n, okay. And once that is done, one can do a Fourier transform of this, and which gives you Hamiltonian. I am not repeating the Fourier transform formula, but all of you know that. So, this is equal to, so minus, this minus sign is there, and there is a k and n, and so there is a t exponential I pi phi by phi 0 n a k n dagger b k n plus t exponential minus I pi phi over phi 0 and a k n dagger b k n and plus a t a k n dagger b k n minus 1 plus a Hermitian conjugate. Okay. So, this Fourier transforming. Okay. If you take this as equation 1 and this as equation 2, so if you Fourier transform 1, you get 2. So, here then we sort of write down the basis as, so the eigenfunction is assumed to be psi of k equal to sum over n alpha k n a k n plus beta k n b k n and so on, and alpha k n and beta k n are amplitudes at A and B sublattices. Okay. So, this is the setting of the problem, that is writing down the tight binding Hamiltonian and including the Piles coupling and where the hopping terms, they pick up a phase, and the argument of the phase includes the A dot dl, or which is nothing but curl A ds, which is nothing dot b dot ds, and that is where one gets a flux from. And then it is of course this can be solved. So, this gives rise to an eigenvalue equation. If I solve with this, solve H psi equal to E psi. Okay. And once you do that, what you get is that a set of equations which is coupled in an alpha and beta. So, this E k alpha k n equal to minus exponential I k a by 2 to t cosine pi phi by phi 0 n minus k a by 2, okay, into this is a beta k n plus a t a beta k n minus 1. So, this is one equation for alpha k n, and this is the other equation for beta k n, which is equal to minus exponential minus I k a by 2 t cosine pi phi over phi 0 n minus K A by 2 alpha K n plus a T alpha K n plus 1. Okay. So, this is quite clear. So, let me in keeping with this equation numbers. So, this is equation 2, you can call this as equation 3 and this as equation 4, and let us call this a set of equations as equation 5. Now, this is a set of coupled equation. There is nothing but the Schrodinger equation written in terms of the amplitudes at the A and B sublattices for the electrons in presence of a external field, and this field gives rise to a magnetic vector potential, and the vector potential modifies or renormalizes the hopping between the nearest neighbor sites. So, once you get this, you solving this, these equations, one should get these have to be numerically solved, there is no other way, and these are for different bands, these are solved, this n is the band index, and what one gets is the following. One gets this energy. So, this is like an eigenvalue equation, and this eigenvalue equation can be solved, and one lands up with this energy as a function of the external flux. And you see that there is a nice symmetry of this, and there are these fractal structures which is not very apparent here, but then if you zoom in at a particular site here, this zoomed in feature looks exactly similar to the entire butterfly. Okay? That is why it is called as a fractal. Once again, just to remind you that the phi over phi 0 has to be a rational fraction of the form p by q. P and q both being their co-prime integers, that is, there is no common factor between them. Okay? So, this is just talking about graphene in presence of a magnetic field, which was needed anyway. We will do quantum Hall effect, and before quantum Hall effect, of course, we need to understand the structure of the Landau levels and details of the Landau levels, its properties, etc. But even before that, I want to speak about a few important things in the context of graphene, and these things are, so some properties of graphene which are basically interesting by themselves, but on the other hand they are also interesting or rather relevant in the context that we are talking about. Okay? We need some experimental ingredients as well, and before we understand graphene, or rather the quantum Hall effect in graphene. A few things that are interesting here is the density of states. Okay? It is not very trivial to get the density of states, because we know that the density of states for a 2D system with parabolic dispersion is a constant. Of course, here we do not have a parabolic dispersion, we have a linear dispersion, Dirac-like dispersion. So, the density of states needs to be figured out. That is one thing. Then we are going to talk about the electron density. Okay. And then we will of course talk about the Fermi energy in graphene. We will also talk about conductivity and so on. As I said, these are precursors of understanding the quantum Hall effect in graphene, and these are in general they are interesting even without the mention of quantum Hall effect. Okay. So, let us just look at the density of states, okay, which we call it as, so density of states is called as DOS. So, how we can get the density of states near the Dirac points? We have worked out the Dirac points in details, and we know that at the Dirac points or in the vicinity of the Dirac points, the dispersion is linear and denotes that of massless Dirac fermions. And in order to do that, this is quite standard, that you equate the total number of electrons with write it in terms of the density of states. Here, of course, we do not have a volume, but we have an area, and this is equal to some 0 to some epsilon and some rho epsilon prime d epsilon prime. Of course, there should be also a Fermi factor inside the integral, but then the Fermi energy or the Fermi distribution is taken to be equal to 1, which is relevant for either you talk about 0 temperature or you talk about low temperature, and the description is only valid if the Fermi energy is very large, and which will show that the Fermi energy is pretty large. It is anything between 4500 to 5000 Kelvin. Okay. So, your rho epsilon prime is the density of states, which is what we want to find. A is the area. So, it is basically it is a areal density that we are, or the total number of electrons divided by this is the areal density. So, n by A is called as the areal density. Okay. So, we are going to integrate this thing from some this expression from 0 to epsilon, till which the linearity of the dispersion holds, and we are not sure, we just keep it as a symbol. So, it is of course valid for low energies, and as you deviate significantly from low energies, this linearity goes down. So, once we know this, we can write this as A and eta, and we will define, of course, there should not be any problem. So, where eta is called as the valley degeneracy. And what I mean by valley degeneracy is that there are two k and k prime points. So, these eta is nothing but equal to 2. Okay. So, this valley degeneracy is included because we want to find the total density of states, and now I convert this energy integral to a momentum, and these momentum is say is a function of the energy. So, I change this rho epsilon prime and I use a dq prime and a d epsilon dq prime. Okay. And why I do that is that, so rho epsilon prime d epsilon prime is written as rho epsilon prime dq prime d epsilon prime and dq prime. Now, the limit of integration, or the range of integration is changed from over epsilon to over q, where q is of course related to epsilon, which is by that linear dispersion that we have talked about. If you want to talk about the spin degeneracy, which is usually not talked about in the case of graphene, but if you include spin orbit coupling, which we will see later, there is also another factor of 2 coming from the electron spin degeneracy, which is nothing but 2s plus 1. For s equal to half, it is 2. All right. So, we have epsilon as going as q. Okay. So, this is what we have learned, that the low energy dispersion is linear. So, we have a d epsilon dq to be equal to constant, okay, which gives of course the velocity. Even though this proportionality looks like that of photon, but of course the proportionality constant is not the speed of light, but rather it is a Fermi velocity of the electrons. So, if I have this equation 1 and this equation 2, then these two can be reconciled if I write down the density of states as q divided by d epsilon dq. Now, if I using epsilon equal to h cross Vf q, this is the Dirac dispersion. Then d epsilon dq becomes equal to a constant, which is nothing but h cross Vf. Even if you write h cross equal to 1, it does not matter, but let us keep it for the time being. And so, from here the rho epsilon it comes out as is like epsilon and then h cross square v f square. This is quite interesting, and it is in contrast with a parabolic dispersion where the density of states is independent of energy, whereas this is a function linearly a function of energy. And so the density of states really behaves like, okay. So this is rho of epsilon and epsilon, okay. So the density of states behaves linearly with epsilon, and this is one of the interesting things, or it's also an important things, because as soon as you try to calculate physical properties, physical quantities, experimentally measurable quantities, the density of states come into the picture, because the density of state dictates that how many carriers there, which are electrons here, how many electrons are there which near the Fermi energy, which would contribute to the, say for example, the transport properties, etc. Okay. So let me go to the next one to calculate the electron density. So what's a typical electron density in graphene? Okay. Is it the same electron density that we talked about in 2D electron gas, such as silicon MOSFET or gallium arsenide, or some structure which is some superlattice structure that we talk about in the context of 2D electron gas? It is in fact something like 2 orders of magnitude more. So let me refer to the original experiment done by Geim, who was awarded the Nobel Prize for discovery of graphene. So this is what graphene is. So this is the SiO2, the silicon oxide substrate. Say this is D, the thickness over which it's grown, and this is graphene. Okay. And there is a sort of voltage that is applied here relative to the back surface, which is, let's call it as Vg, and this D is usually of the order of 300 nanometers. So graphene is grown on that, on this substrate. SiO2 is the substrate, and in addition to that, what you have done is that you have applied a gate voltage with respect to the bottom part of this thing. So this looks like a capacitor that is formed, and we know that what is the capacitance of a capacitor? The capacitance of such a capacitor is its C is equal to epsilon A over D, okay, where A is the area, and epsilon is the dielectric constant of SiO2, okay. And of course A is the area, as I said, and D is the thickness, which is written here. So if you want to calculate the carrier density, Ne, this is equal to CVG by E, where Vg is the gate voltage. So this is equal to epsilon by dE and a Vg. So for a Vg of about 100 volts, Ne comes out to be about 10 to the power 12 to 10 to the power 13 per centimeter square. So this is the typical electron density that is found, and this is at least 2 orders of magnitude more. Okay. So this is an important thing, but there is another thing that's very important here, which was not there in the 2D electron gas. You see, as Vg is increased, okay, Ne can be made larger. That is the electron density at the Fermi level that can be made larger by applying larger gate voltage. And not only that, the sign of Vg would determine so that any can be both positive and negative. So, you can have positive charge density or negative charge density depending on the sign of Vg. There is also an important point. Okay. So, let us just look at the Fermi energy quickly. So, this is the third point is Fermi energy. Okay. So, the Fermi energy can be obtained in the following fashion. We have already worked out that the density of states is linearly proportional to epsilon. So, rho epsilon is equal to epsilon, and then Ne, which goes as epsilon f square. So, that is basically the 2D feature. So, Ne goes as epsilon f square, which tells you that this is like a Qf or Kf square, which is the Fermi wave vector square. Because there is a linear dispersion, this is unlike parabolic dispersion. So, epsilon f is then proportional to root over Ne. Okay. So, which means that the Fermi energy depends on the electron density, and for an electron density, just to have a square root, let us take Ne equal to, say for example 10 to the power 12 per centimeter square. We have of course written as 10 to the power 13 in the last slide, but just to have no confusion with the square root, let us just take it as 10 to the power 12, which I will be able to do a square root. So, this epsilon f turns out to be something around 4.5 electron volt. So, this is the value of the Fermi energy in graphene. Okay. And so, this 4.5 electron volt is pretty large, and if you consider the corresponding Fermi temperature, that is very large. So, this means that graphene is a highly degenerate system at room temperature, because room temperatures can also be taken as almost like 0 Kelvin, and at 0 Kelvin the system is actually a degenerate Fermi gas. Okay. And then let us look at the conductivity of graphene. And the conductivity can be obtained from the Drude formula, which is equal to, so this is a Drude formula, and this Ne is the electron density, E is the electronic charge, and mu is the mobility, which is known to be very high for graphene. So, mu can be defined using the relaxation time, which is equal to E tau over mf, where mf is the mass of the carriers at the Fermi energy. Okay. And so, the tau is the relaxation time. So, relaxation time, just to remind you that it is the time between two successive collisions. Okay. So, here it shows that mf is actually not a constant, but it depends on the electron density. Okay. If we use the mean free path, the definition of mean free path, which is say mfp divided by vf. So, LMFP is the mean free path. And Vf is the Fermi velocity. Okay. So, this is tau. So, mu becomes equal to E LMFP by putting this tau expression on the top, and this is equal to a Vf MF. Okay. So, that tells you that the sigma, it becomes equal to E square over h, which is the scale of the conductivity or the conductance. So, this is equal to LMFP into root over NE, and so which means that sigma is proportional to root over of NE. So, this is the dependency of the conductivity on the electron density. This can be also written as so this is like E square over H and a Kf, which is a Fermi wave vector, and the LMFP. This is a dimensionless quantity if you see, because your Kf has a dimension of inverse of length, and LMFP has of course the dimension of length. That will tell you that they will cancel each other. Okay. So, now of course, we will do a derivation of Landau levels in graphene, and how would we do that? We will just plug in this minimal coupling or the Piles coupling into the Schrodinger equation with a particular choice of the gauge, and then solve for the energies, and these energies will be the Landau level energies. Exactly, we have done the same thing. However, in 2D electron gas, we have talked about the electrons to be in continuum. Now, we are not talking about electrons to be in continuum. The electrons are confined to a lattice geometry, or rather 2D honeycomb lattice geometry, and the problem is further compounded by the fact that there are two sublattices A and B, both corresponding to of course the carbon atoms, but this will give you a structure 2 by 2 structure. And if in addition to the 2 by 2 structure, if you take into account the Valley degeneracy, that is the physics occurring at both the k and k prime points together, then the size of the Hilbert space or the size of the Hamiltonian matrix goes from 2 by 2 to 4 by 4. And of course, in some situations which we will encounter later, that if you have a spin orbit coupling, that is spin is coupling to the orbit, then we cannot talk about spin polarized electrons anymore, and we have to talk about each spin separately. Incidentally, here, just like the 2D electron gas, the Zeeman effect is negligible. Okay. The Zeeman effect means the Zeeman effect, if you remember that the Zeeman energy is Ez equal to G mu B B. Okay. G is called as the Landau factor. This has been discussed in the context of 2D electron gas, but I am still renewing those discussion here. And so, this is usually equal to 2 for electrons in graphene, and this is then it's equal to EH cross over M into B. So, in principle, you know, because the Landau levels are the Landau levels also have this as n plus half, only talking about H cross omega B, this 2 DEG. Okay. So, the scale is set by H cross omega B, and so omega B, if you remember, it's equal to EB over M. So, these EL, L and EZ are of the same order, but actually in experiments it does not happen. In fact, EZ, which is the Zeeman energy scale, is much smaller, and it is for that reason that we can still ignore the presence of electronic spin into the problem, because in fact in a 2D electron gas it can be shown that which we have done in some sense, that the nth Landau level for upspin, it coincides with, say for example, n plus 1th Landau level for the downspin. So, there is basically a degeneracy, and then this spin really does not count much into that discussion. And same here, unless one has a strong spin orbit coupling, there is no need to talk about spin. So, we will be mostly happy with a 4 by 4 Hamiltonian to be solved instead of a single expression for the Hamiltonian, which we have done for the 2D electron gas. So, we have taken a Hamiltonian, solved it for a given gauge, and we got the eigenfunctions and eigenvalues, and these eigenvalues came out to be just this. Okay. However, these things are going to be more complicated. There is a matrix structure to the eigenvalue equation, and hence you have to diagonalize the matrix in order to find the eigenvalues, and their dependencies on these n, the Landau level index, will have to be found out. And it turns out that the Landau level index does not have the same structure as it's here. So, we will see this in the subsequent discussion, that this Landau level does not go with n, but it goes with root over n. And in fact, it sort of goes as root over n into b. There is a mod of n that I have written. If you notice, this mod of n means there are positive and negative values of n that are allowed, which is again unlike the one that we have done for the case of 2D electron gas. Okay. So, this are going to be coming up, and once when we understand the structure of the Landau levels and their properties, doing quantum Hall effect is only doing a Kubo formula, putting it in a Kubo formula, which we have seen elaborately, that putting that into the Kubo formula, these wave functions and energies, and then getting this Hall conductance out. And just like 2D electron gas, we will see that these plateaus are quantized, but the quantization is not same as they are for the electron gas. In fact, there is a half integer quantization, and also the width between successive Landau levels in terms of temperature, these are very large. So, these are very large numbers, which goes on to say that these Landau levels or quantum Hall effect in graphene should be realizable at room temperature. So, first we will talk about the obtaining the Landau levels, and I will be doing a rigorous derivation of obtaining the Landau levels. As I said, that it is not that straightforward as it was for the 2D electron gas. So, you have to be careful and watchful on the derivation, so that you can recreate it, or rather you can reproduce it on your own, and then we will talk about the quantum Hall effect. We will not undergo through again a rigorous derivation of the Kubo formula, but we will simply state the results of the quantization of Hall conductance in graphene.